Hey everyone, I'm Anish and welcome back to PrepFusion. So today we'll be starting the lecture 6 of border plots. So in the previous lecture, we learned how to basically plot the border plot similar along those lines, and like we learned about simple repeated poles. Basically when I have n real repeated poles, what happens to my border gain plot and what happens to my border phase plot. The gain plot, the slope simply becomes a multiple of that. For one pole, you're getting minus 20 dB per decade. For two poles, how much you get? Obviously minus 40 dB per decade. It's just simple analogy. For 1 0 you're getting plus 20 dB per decade. For 2 zeros, how much you will get? Plus 40 dB per decade. Okay, that is one thing, and this was a summary basically. And the phase plot will also have slope of minus 45 n per degree per decade and plus 45 m degree per decade. Okay, these two things. So this is one thing, and I gave you homework of these two transfer functions. Okay, so but before that, before solving these two, I want to solve another thing. What is the other thing? Basically I want to solve for the dc gain of a transfer function. Okay, dc gain of a transfer. What do we mean by dc gain of a transfer function? We have already done this in chapter 1, but still I want to repeat it here to explain you one thing. Also what we'll do in this lecture, we'll do the recovery of transfer function from asymptotic Bode magnitude plot. So that this is the most important one. Okay, most important, whatever we have been building, right, whatever we have been studying till now, we have been studying to solve this, because in questions, in examination, questions will come from these topic, only from these topic. When we will solve this, we'll understand. We have to recover the transfer function, like the Bode plot will be given, Bode magnitude plot will be given, and we have to recover the transfer function from that, not the other way around. What we have been doing till now is the opposite. We have been given the transfer function and we have been plotting the Bode plot for that one. Now we have to do the opposite. Okay, but obviously first you will be expert on the first case, then only you can solve for the second case. So asymptotic Bode magnitude plot, and here, so this is the most important part. Most important. Okay, because questions mainly come from here. So first let us understand the comparison between dc gain. Okay, what do you mean by dc gain of a transfer function? So here we have been given two transfer function and we have to find the dc gain for this one. What is dc gain? Dc gain is simply what g of s at s equals to 0, magnitude of g of s at s equals to 0. So this is what my dc gain is. Okay, so for the first case, what is my dc gain? So you just copy this transfer function, dc gain of g1 of s equals to 0 into 0 plus 1 divided by 0 plus 1 into 0. This is simply in time constant format, general time constant. Obviously this will be my dc gain itself, right? If this wasn't in time constant format, then we had to convert few things, make it to the general format, then we could have done, or simply you could put s equals to 0 there, that also will give you the dc gain. So dc gain is 100 in this case. Now for the second case, what is my dc gain? Let me take another page. Second case, my dc gain is g2 of s. So here, as we have two poles at the origin, what do you do? Like you can't simply put s equal to 0. So what you will do? You will do something like this. Like I have seen people do something like this. The dc gain is limit s tend to 0 s square, as you have two poles at the origin, so you will remove that pole and then you put s equals to 0. So after that, what you get? You get 1 only. Now is this correct? This is not correct. Okay, look, this is the definition for what? This was the definition for acceleration error coefficient. If you recall correctly, like this was in the steady state error chapter. This was definition for acceleration error coefficient. Okay, but this is not the DC gain. What is the DC gain? Obviously the DC gain is infinite for this case, because if you put s equals 0, it is going to infinity. So DC gain is infinity. Okay, so we don't write the DC gain for this one because DC gain is undefined because it's infinity. Okay, so DC gain is infinity for this. Infinity. Okay, and what about in dBs? In dBs it is also infinity, because you do 20 log base 10 of infinity, you get infinity itself. So yeah, it is also infinity. Now let me take another small example, example that, let's say you have been given transfer function like this, g3, this is extra, g3 of s equals to s into s plus 1, s plus 2, into s plus 3. Now what is the DC gain for this one? You will say, sir, I will remove this 0 at s equals to 0, then I will put s equals to 0. It will be 1 by 6. No, the DC gain here is at 1 by 6. What is the DC gain? DC gain here is simply 0. You put s equals to 0. Okay, DC gain will be 0 because 0 times anything is 0 itself. Zero. Okay, DC gain here is 0. So in log, what is it? In log, so in log terms, log base 10 of 0 will be what? Minus infinity. Okay, mathematically it is minus infinity. So like I wanted to clear one thing, that here we were starting from somewhere, right? Like maybe I forgot, yeah, here. So from where we are starting, as we have poles, right? So we are starting from positive infinity, and this 0 omega equals 0 doesn't even exist here. That's why we're starting from positive infinity, and it is coming down from positive infinity. Okay, that's why this is like this. So we don't know, like at omega 0 it is coming from positive infinity, and we don't even have omega 0 in this omega axis because it's in log scale. Okay, that's why. So we are coming from very high value. And why is this like this? Because we're coming from very low value, negative infinity. This is in dBs. This is in dBs. This is in dBs. All this is in dBs. That's why we're coming from very low value, infinity, negative infinity, and this is coming from positive infinity. So yeah, that's the main thing. That is the main thing that like I skipped in the explanation of the this part, right? This is why this graph is like this and this graph is like this. So yeah, this is one thing. Now let's come back to this question. We have to solve this question, right? So here also we have a 0 at s equals to 0. So obviously we have to solve this. So yeah, let's start with this transfer function. So first, like I told you a few steps, how to use those steps. So first what you'll do, you will convert this into general time constant format. So 15th question. You take common 4 square, so this is s plus 1 by 4. Okay, to find the corner frequency also. And this is getting multiplied with 8 times 2. Basically 8 is taken common and 2 is also taken common. Here 4 square is taken common. Okay, so this is 16 by 16, so this is 1 itself. So here what is my DC again? It is 1. No, it is infinity, right? Because here we have a pole at s equals to 0. So s by 4 plus 1. So at omega equals to 0, we don't have any, like we can't define that gain, it is infinity. S by 2 plus 1 S by 8 plus 1. Okay, so we got the corner frequencies, like the corner frequencies can be identified from here. So we have 1 0 omega z equals to 4 radian per second, and we have two poles, omega p1 and omega p1 equals to 2 radian per second, and omega p2. Equals to 8 radian per second. So these are my poles. Obviously I have another pole at 0 radian per second, single pole. So due to all this we'll get minus 20 dB per decade slope, and due to this plus 20 dB per decade slope. Okay, sorry, I had two poles here, sorry, so two zeros here, sorry. So this will be square, so these are times 2. I will do multiplied by 2, as I have two zeros here. So I will get plus 40 dB per decade slope for this one. So how will my graph look like? So I will generally, what is the convention is, I told you previously also that we start from, like obviously we can't plot for omega equals to 0 in this log scale. So we'll plot for 0.1. We'll start from 0.1 radian per second. Okay, and this is the magnitude of g of j omega. In dBs. Okay, so now what is happening now, like at omega equals to 0.1, what is the gain? How can we find the gain? So here what we can assume is that as all the corner frequencies are much greater than 0.1, so the magnitude due to this, the magnitude due to this, and the magnitude due to this can be ignored. Like you calculate it for yourself. You put s equals j omega, then what do you do? Omega square by 4 omega by 4 whole square plus 1, and if omega is 0.1, it becomes much lower than this one. So obviously we can ignore. Already we have done this low frequency approximation I'm talking about. So this magnitude due to this, magnitude due to this, magnitude due to this can be ignored because I have a plus 1 here. But magnitude due to this cannot be ignored because I don't have a plus 1 here. Okay, I have plus 0 here. So the magnitude of this one will be dominating. So what is the magnitude of this? Simply omega itself. So the magnitude due to all this can be ignored at 0.1 radian of frequency because all the corner frequency are much greater than the this 0.1 radian per 0.1 frequency. So what I can say, I'll copy this. Like you calculate for yourself that magnitude due to all the corner frequencies can be ignored. Now obviously if they wouldn't have been much like if the corner frequencies were near, then we wouldn't have been able to ignore. Okay, so then what we would have done is we would have reduced our this initial starting frequency. Like here we are starting from 0.1, then we would have started from 0.01 or something to simplify our graph. Okay, to simplify that value calculation here, whatever value we get. As this 0.1 is much less than the corner frequencies. Okay, but this can't be ignored. Remember, this one can't be ignored. Obviously the pole or 0 at s equals 0 can't be ignored. This can't be ignored. Okay, so yeah, this is the case. This is the case basically. So now what we should do? Now basically this kind of, now let's start. So what is the magnitude at 0.1? So magnitude at 0.1 will be all this can be ignored. So you just put magnitude of j omega equals to at omega equals to 0.1. So this is a shortcut basically that we do. Obviously you can put 0.1 everywhere and then calculate the magnitude. That will be slow method. I'm just teaching you the shortcut. So this will be 1 by 0.1. So this is 10 itself. Now in dBs, what will this will be? This will be 20 dBs. 20 dBs. Okay. So yeah, this is in decimal scale and this is in dB scale. So we'll start from like this 20. Obviously we're not starting, it is starting from plus infinity. We can't show it in the graph obviously here. So we'll start from 20 dBs. Okay, and let me mark the corner frequencies. It is 0.1. Then what is it? So then we have 2, 4 and 8. 2, 4 and 8. So now what is happening? Now so we have one pole, like s equals to 0 we have pole. Then after 2 what is happening? After 2 we have again another pole. So we again have another pole. Remember, right, this axis is starting from 0.1 radian per second. Again another pole, and then what do we have? We have a 0. We have two zeros. So like now what is the slope? This is minus 20 dB per decade. This slope is minus 20 dB per decade. Now we had another pole at s equals to 2. So this slope becomes minus 40 dB per decade. Now again, what do we have? We have a 2 zeros at this point. So obviously this will get added. This slope will get added to plus 40 dB per decade. So overall my slope will become 0. So this will become plus 40 dB per decade. And at s equals to 8, we have another pole. So it will become minus 20 dB per decade. This is minus 20 per decade. So this is how you solve basically. You don't draw the tables around for Bode magnitude because Bode magnitude plot is very simple to plot and we don't need to plot tables for this. So now this is the Bode magnitude plot. Let's go for the next question. Next question is this one. There we had a pole at s equals to 0. Here we have a pole at s equals to 0 at s equals to 0. So here obviously we won't start from like s equals to 0. What we'll do is omega is 0. First we'll convert this into standard time constant format. So what is my standard time constant format? So standard time constant format is this. This time things will change a bit. Gh of s. Previously was it like if I write in terms of g only g, please ignore. Okay, here this will be gh of s. Okay, please ignore like if I just write h or something. Sometime I get like forget to write gh. This all will be also gh. Don't get confused if I forget to write the gh term. Okay, gh, everything is a variable. Doesn't matter what you name them. So this, right, if we now take like s is here and then we have to take common 10, s by 10 plus 1, then we have to take 400 square common. This one becomes s by 400 plus 1, and this one becomes s by 1000 and also we have to take 1000 common. So this again from the denominator we take 2 common, so to take 2 common actually, so 2 square will get common because like this is square term, s by 2 plus 1 into 20 into s by 20 plus 1 into 100 cube s by 100 plus 1. Okay, so let me just simplify this. So overall how much I have in the numerator, like the factors I'm talking about, the numbers I'm talking about. So this is 10, this is 100 square, which is like 4. I will talk about that later. 100 square, which means 10 to the power 4. So 10 and 10 to the power 4 into 10 to the power 3. So 10 to the power 4 into 10 to the power 4, which is 10 to the power 8. So overall I have like power of 10 is 8. And what else I have? I have 400 square. So this is 400 square actually. So this is 4 square. Like I have already taken the zeros. Now 4. I have to consider the 4. So 4 square, which is 16. Or I can say this as 2 to the power 4. Same, right? So I can just use this. To the power 4. Now here, what is happening here? We have a 2 square term here and another 2 and nothing. No 2 term again. So we have total 2 cube into what? This 10 into 100, or like we have 10 to the power 2 whole cube. So 10 to the power 6. This 10 is also here. So it is 10 to the power 7 here in the denominator. 10 to the power 7. Okay, so this is 10 to the power 7 and this is less. So this 10 to the power 7, it's getting cancelled here. So this is only 10 and this 2 cube is getting cancelled here. So this is 20. This is 20. So overall I have 20 here. Okay, so let me use the next page. What can I write my g of h of s as? So overall in the numerator I have 20 and this is s into s plus 10 by 1 into s by 400 into s by 1000. Okay, then divided by, okay, this is a square. I forgot to write square over here. This is a cube. Okay, this is also a square. Okay, sorry, I forgot to write the squares and cubes. This is a square. This is s by 2 plus 1 it's whole square. This is s by 20 plus 1. This is s by 100 plus 1 whole cube. Okay, so these are the things basically. So now what else we have? So basically, so now if you want to do the Bode plot for this one, so Bode plot for this one, first we have to write the gain at s equals to 0.1, right? And as all the corner frequencies are much greater than 0.1, so what we can do is magnitude of g of h of j omega at s equals to j 0.1. What is it? Simply all this will be ignored, this will be remained. So obviously 20 times 0.1, so 20 times 0.1 is this is 2, and in dB scale 20 log base 10 into like 20 log base 10 2 is, or 20 times 0.3, which is 6 dBs. So at 0.1 we have 6 dB. Okay, then obviously we have a 0, so it will increase further from there. Okay, so yeah, let's plot that basically. So here, let me just copy this graph again. Just copy this. Remember, all this is in log scale, like the omega is in log scale, x-axis. Okay, so basically, like, where are my this corner frequencies? So one is at 2, then we have at 10. So this is at 10. So let me mark the corner frequencies. This will be difficult for to draw. 2, 10, then 20. Then how many we have? We have 100. Then we have 400. And then we have 1000. Okay, so 400,000. Now let's draw. So we will start from what? We'll start from 6 dBs. 6 dBs will start. Okay. Okay, then what is happening? We have a 0. So obviously the slope is plus 20. Plus 20. Make the slope like this. Okay, let me write this also. Slope is plus 20. Then what is happening? Then after this 2 we have a okay, sorry, after this 0.1 we have what? 2 poles at omega equals to 2. So we have 2 poles at omega equals to 2. So obviously this one was plus 20. So one pole will make it 0 dBs, another pole will make it minus 20. So slope will change to minus 20 until this 10 radian per second. Then what is happening? After it changes to minus 20 dB per decade, what is happening? After it changes to minus 20 dB per decade, then at s equals to 10 we get a 0. So it will again contribute a plus 20 per decade slope. So here plus 20 dB per decade minus 20 which is 0. So obviously slope will be 0 now until this 20. So this is 0 dB per decade. Now until 20, after 20 what is happening? 20 we are getting another pole. So again it will contribute minus 20 per decade slope. So this will be minus 20 dB per decade. Okay, after this what is happening? After this, after 100, like we're getting 3 poles. So it will total contribute minus 60 per decade. Only this. So we currently have the slope of minus 20 dB per decade, and it is contributing another slope of minus 60 dB per decade. So overall I will get minus 80 dB per decade. Overall I will get minus 80 dB per decade. So this will be very sharp this will be. Okay, and this will contribute minus 80 dB per decade. Okay, next after 400 what is happening? I am getting 2 zeros. So currently I have minus 80, 2 zeros will contribute plus 40. So this will become plus 40 dB per decade. So plus 40 dB per decade. So this will be something like this. Okay, and this is plus 40 dB per decade. Sorry, not plus, I mean minus 40 dB per decade, but this is contributing plus 40 dB per decade at this corner frequency, the zeros. And after this what is happening? At 1000 we are getting another 0. So this will contribute plus another plus 20 dB per decade. So the overall my slope will be minus 20 dB per decade. So it will be something like this. Now is this correct? Let's check, right? So I'm ending with minus 20 per decade. So again use that formula that the ending slope will be minus 20 into n minus m. So how many poles we have? We have 6 poles. How many zeros we have? We have 1, 2, 4 and 5. So n minus m is 6 minus 5 is 1 into minus 20 is minus 20 itself. So yes, from there you can cross verify that you are correct. Obviously drawing the phase plot will be very difficult and very time consuming for this, so we won't draw. At max the phase plot there will be 3 corner frequencies. That is what I assume. Okay, that is what I assume. Like if phase plot comes in the gate examination, 4 corner frequencies may also come, but it will be too much hectic. Okay, so these were the homework questions. Now let's come to the topic of this lecture, that is to identify transfer functions using the Bode gain plot. So first let's do few examples and from there we'll understand. Okay, so like this is the first question. So here the asymptotic approximation of the log magnitude versus frequency plot of a minimum phase system. Basically asymptotic approximation means the Bode plot they are talking about. So versus the log magnitude and the frequency plot, and this scale is in, remember this scale is in decade scale. Scale is decade scale, don't forget, decade scale. That's why this is straight line, right? That's why. Of a minimum phase system with real poles and 1 0 is shown in figure. So its transfer function will be, what will be its transfer function? So minimum phase system is, it is given that it is a minimum phase system, and we have to identify the transfer function from this by just seeing the Bode gain plot. Can you identify it? Now they have given you the options. Okay, they have given you the options. So from the options also you can understand few things. Okay, understand few things. So initially, like they are telling me, it is starting from minus 40 dB per decade. It is starting from minus 20 per 40 dB per decade. What does this means? This means I have two poles at the origin. At that instant, I got to know that I have two poles at the origin just by seeing here. So two poles at the origin, only C and D option are matching. So C and D option are matching. These can't happen. Okay, so these are automatically eliminated. Okay, now what next? After this, I have a like this becomes minus 60 dB per decade. From minus 40 dB per decade, this becomes minus 60 dB per decade at omega equals to 2. So obviously my slope reduces. That means I have pole slope reduces by 20 dB per decade. That means I have only a single pole at this 2 location. So here, yeah, this is also a single pole and this is also single pole. That is fine. And this is also same. This is also same. This is also same. This is also same. So everything is same for these two. Only this coefficient, like that, this DC gain, like this is not even the DC gain. This is K. Value of K is change. Value of K change. So for value of K, this hint is given. So we have to now use this hint. Okay, we just simply can't use this one. Simply can't use this one. Okay, so how to use this one? So what you can do is, I told you, right? I told you that like this is from the options itself. This is from the option itself. But first let's solve it from the basics. So then I will show you how to eliminate the options. Like I've already shown you the half portion I will show you next. Now the corner frequencies, what are the corner frequencies? Here, as I can observe, at omega equals 2 I have one pole, at omega equals to 5 I have 1 0, because it changes from minus 60 to minus 40, so slope gets added, so I have 1 0. Then at omega equals 25 again I have one pole, so I can write like the form of like standard time constant format g of h of s, like this, k into, so first I have obviously two poles, that is for fixed, two poles are fixed, that is one thing, because it starts from minus 40 dB per decade slope. Then at omega equals to 2 I have again one pole, so this is s by 2 plus 1. Then at omega equals to 5 I have 1 0. Then at omega equals to 25 I have another pole, omega equals 25 I have another pole. So here I have another pole. Okay, so these are the poles and zeros. So yeah, this is the thing. So now what you do is, so this is a standard form, and this is a form that is not given over here. This form is not given over here, so we can't do this. But first let's find the value of k. How will we find the value of k? What you can do is, like, you have to find it, the magnitude at 0.1 is given 54 dBs. So here, what is the magnitude at 0.1? The magnitude at 0.1 is simply, we can ignore all this because the corner frequencies are much greater than 0.1. So this will become simply k by omega square, okay, or k by omega square, or equals to k by 0.1 whole square. Okay, so if this is k by 0.1 whole square, what does this become? So this is k into 10 square. Okay, now we have to convert this into log scale. You can either convert this into log scale, or you can convert that into absolute scale. So what we can do, it is given as 54 dBs. Now if it is given as 54 dBs, so in absolute scale, what will be the value? 20 log of x equals to 54. Now my x will be simply 10 raised to power 2.7. This will be my x. Now what is 10 raised to power 2.7? Let me just find it out. Something 10 raised to power 2 power 7. Yeah, it's around 501, or like approximate it as 500, because the answer will be something like this. So now what we do is, this value we put here, okay. This is equals to x itself in absolute scale. So k equals to 0.1 square into 500, so it becomes 5. So k is equals to 5. Now 5 isn't even given in the options, because like this is not in the standard time constant format. We have to convert this into whatever this format is, simple format. So k is 5, so again we have to multiply by 5 everywhere, right? So multiply 5 in the numerator. No, like we have to just do one thing, just take add this one up, right? Add this one up. So what I will do is, k is 5, that is fine. My g of h of s, k is fine, 5. This is s plus 5, add these two up by 5 divided by this s square, this s plus 2 divided by 2, and this is s plus 25 divided by 25. Okay, so this 5 cancels out and this 2 into 25 goes above, so this becomes 50 into s plus 5, okay, divided by s square, s plus 2 into s plus 25. So this is my answer. So which option is matching? So basically g of h of s is this, and option I think B, what was it? No, option D is matching. Okay, so like here can we do this using the shortcut formula? Unfortunately no, we can't use this like any shortcut, like without any short, like we have to do this, like we have to write this one down, then we have to find the value of k only. Like what you would have done is, you got to eliminate these two options and directly found the value of k here. You don't need to write all this, right? Because you already know, like if you know the concept, then you don't need to write all this. You directly come here, you find the value of k, then you directly put you directly put the value of k here and then solve. Okay, so it will take you like 1 minute or 1.5 minutes. So yeah, if you know all the concepts, obviously. If you don't know, then it's fine, so you can solve solely. So this was the concept of this question. Like I took this question just because of this slope, right? We have a slope here, and this 54 dB is not the DC gain. This 54 dB is not the DC gain. Do remember, this doesn't even have a DC gain. Like DC gain is undefined for this one because it is coming from infinity. Okay, the gain at 0.1 is defined for this one, and we can approximate this one because the gain due to all these components will be 0. Gain due to all this will be not 0, will be simply 1, because 0.1, like here 0.1 by 5 whole square plus 1 will dominate, so this will be 1. 0.1 by 2 whole square plus 1 will dominate again for the same thing. Okay, that's why only these things will remain and other things we can ignore. Okay, so yeah, this is the about the question, and with this question now I want to come to the steps. So I didn't come to the steps first because I want to tell you that you don't need to remember steps, you can directly jump in the question. But obviously if there is there are step-by-step process, so it is easier for you to recall that yes, I know this step, yes, all these things. So before we solve the question, now we'll understand how to identify transfer function from Bode plot. What are the step-by-step procedure? First step is identify the corner frequencies. Here we identified the corner frequencies, right? Wherever there is slope change, there will be corner frequencies. Now observe the initial slope. Sorry, this is not initial slope. Observe the initial slope. Okay, it gives the number of poles or zeros at the origin. So if the initial slope here, it is what? It is minus 40. This means it is number of poles is 2 at the origin. If the initial slope was plus 20, it means I have single 0 at the origin. Depends. whatever slope initially we are getting, it is either coming from plus infinity or minus infinity. So if it's coming from minus infinity, obviously there is a 0. If it is coming from plus infinity, there is a pole. So this is about the initial slope. Now determine the change in slope at each corner frequency. How much slope is changing? Now the delta slope will be equals to minus 20 times n. If the slope is reducing, okay, by 20 times n, that means there are n poles at the location, or 6 n dB per octave. So I haven't we have converted decade to octave, so I will tell you how do we get 20 dB per decade into octave. That I will tell you. Okay, that we will understand. So first let me here write how to conversion, the scale conversion, the dB to octave. So what we know that 1 decade, I have proved already this, that 1 decade is equals to 10 by 3 octave. So I have to cover thrice in octave scale to cover 1 decade. 1 decade is bigger than this. So this is how to convert this 20 dB per decade into octave scale. This is 20 dB per decade. Okay, so simply just replace this decade by 10 by 3, because this is one decade, right? So this is what, 20 dB by 1 decade. So you convert this 20 dB by 10 by 3 octave, because 1 decade is 1 decade is 1 decade is 10 by 3 octave. So now this becomes 60 by 10 decade per octave, dB per octave. So this is 6 dB per octave. Okay, so yeah, this is how you convert from 20 dB per decade to octave. So this is what here it is written. Okay, so yeah, if you if it is minus 20 n, so we have pole of order n at that corner frequency, pole of order n at that frequency. And here we have 0 of order m at that frequency. Okay, so these are the things basically. So now next we have to find the value of k. Now k, we can find if the gain at any frequency is given in the magnitude plot. What we did, we equated this one, right? We equated this here, the gain at 0.1 was given, so we found the magnitude. So value of k can be found out from that, or we'll do this with question if you don't understand this statement yet, that if the intersection of a line with the omega axis is given, then we put the value of omega in the approximate transfer function and equate it with 1 and find the value of k. What do we mean by this? So obviously if you know this one, so here we have solved one thing, right? So here wherever there is intersection with the 0 dB axis, 0 dB with this slope, okay, then if we just put simply value of k, we'll get our value of k. If you know the value of omega, then we'll get our value of k from this relation. Okay, we'll solve one question from there also, we'll understand. So that's how we find the value of k. We will solve one question from there, we'll understand. Now next is write the transfer function with all poles and 0 in time constant form. Already told, and dissecant. So already told this one. This is simple, what is time constant form and stuff. And if in the question they are giving you in some other form, so you have to convert it back to other form. For Bode plots, we always use this general time constant form. This is very simple. So now let's solve a question. So this is the question. So this is a GATE 2013 question, and here we have to find the Bode plot of a transfer function g of s is shown. The Bode plot is shown, and they are giving the gain in dB scale is 30 dBs at omega equals to 1 and minus 8 dBs at omega equals to 10 radian per second. The phase is negative for all omega, so it is telling me minimum phase system only. And then g of s is what? The phase is negative for all whereas omega means there isn't any zero. Then we have to find the g of s. What is my g of s? Now first thing what I observe, if I observe from the question itself, that I am moving one decade from 1 to 10 times. I'm moving one decade, and how much I'm moving in the y-axis. How much dBs I'm moving? I'm moving 32 in minus it. So total I'm moving 40 dBs. So I'm moving in one decade, I'm moving 40 dBs. So 40 dB per decade. So what happens when the initially the slope is 40 dB per decade? It means I have two poles, 20 times 2. So two poles at the origin. Two poles at the origin. So this option gets eliminated. This option gets eliminated. So only this and this option remain. Okay, this is this and this option can happen. This option and this option. Now out of this, which one is true? Now obviously, if this is 32 over here, this is in dB scale and this is in absolute scale. Obviously this 32 can't be here, so 39 will be my correct answer. So if you are in a hurry and stuff, so you can directly take this one and move on, or you are just ending the exam, you can take this. Obviously we'll solve this in the proper method. We'll not do any assumptions and trick things. So how to solve this one? So here, how to find the value of k. How to find the value of k? So they have given the value of the gain at omega equals to 1. So you can use that, or you can use the slope method also. So obviously, let's do this first. So how to find the value of k? So they have given what we understand, the slope is minus 40 per decade. If you don't want to, if you didn't wasn't able to catch it, so let's do it manually. So what is my slope AB formula? It is here. My slope is A and B. Okay, slope AB equals to this, which is YB minus YA divided by log of omega B by omega A. Okay, so what is my A? A is 1 radian, B is 10 radian, and here what is my magnitude? 32, and here magnitude is minus 8. So minus 8 minus 32 divided by log of omega B by omega A. What is omega B? Omega B is 10. Omega, this is base 10. Base 10. So this becomes simply what? Minus 40 dB per decade. You can check, if you couldn't understand that, how is it minus 40 dB per decade? This is minus 40 dB per decade. Now how to get the value of k? How to find the value of k? So how to find the value of k? So if you want to find the value of k, what you can do is that we can approximate our transfer function like this: g of s equals to k of s square. So if it is equals to k of s square, what does this mean? So this is k by, now at omega goes to 1, we have been given the value. Okay, so either what you can do, either you can calculate this in log scale or in simple scale. So magnitude will be g of j omega k by omega square. So in log scale, what does this mean? In log scale, (20 log k minus 20 log omega square). Now whenever omega equals to 1 is given, that means you're given 20 log k, because here we solved this question. If you want to remember that, well and good. If you don't want to remember that, don't need to remember that, totally fine. So here if you recall that what is it here. So always at omega equals to 1, you got 20 log k value. Whenever, whatever may be the square power, whatever may be the power, the cube square, whatever the power, omega equals to 1, you always got 20 log k. So you can directly equate that. If you're fast, obviously you can directly equate that. If you're slow, you need to go step by step. Now we are slow, obviously, That's why slowly learning now right now, so that's why we're going slow. When we'll solve like questions, we'll go very fast. So this is 20 log omega square. So this is 20 log omega square. This becomes like omega at omega goes to 1. I'm getting 54 dB, and this is 20 log base 10, and this is minus 0. So k is simply equals to 10 raised to power 2.7. Okay, and okay, this is 54. Sorry, this is 30. Sorry. This is 32. Sorry, 54 was the previous question. It is 1.6. So let me just do this. 10 raised to power 1.6. It is 39.82 almost, or 81 you can say. So this is the answer basically. So here like you can write that 39.8. So this is correct, and this is also not correct. So this is correct. Like from here you can find out, or if you don't want to find out from here, what you can do is like it's just the same thing only. What you can do is like simply you convert this one into absolute scale. Okay, 32 into absolute scale. So you convert this 32 dB into absolute scale. So this is 10 raised to power 1.6. Now you equate this one with k by 1 square. Okay, because at omega goes to 1 you know the value. Okay, or if you want to find the value of k from here also you can find that. You convert this into absolute scale. So this one minus 8 dB minus 8 dB into absolute scale. So this is 10 raised to power minus 0.4. So like 8 divided by 20 minus 0.4, and you equate this one with k by 10 square, because omega is 10 right now. So now you get the value of k. So you will get the same. I'm just cross verifying. Into 100. So you get the same value, 39.81 itself. From here also you get the same value, k equals to 39.81. So whatever you do, that's what the first step was telling me, that if the gain at any frequency is given, you just equate that approximate transfer function at the frequency and gain from that part. Okay, simple only. So this is what the first thing is giving. Now with respect to omega axis, what do you mean if the intersection of the line is with respect to omega axis? This will understand in the next question. So this was a gate question, good question. And here, okay, just hold on a second. Yeah, we have the another question. So this is also a gate question. I don't remember like which. Yeah, this is 2014. Just written. This is 2014. So gate. I don't remember if this E or something. So this is 2014. Okay. Now, if the Bode magnitude plot of the transfer function is given like this, you have to find a by bk. All these unknowns you have to find. So for you to find these unknowns, you can't use any tricks or shortcuts, because this time NAD has come up, so you can't eliminate options. You have to go by the basics now. So how to solve this by the basics? First thing is you mark this is giving in octave, so you convert this into decade scale, or you can use this octave scale also. Why? Because here multiple of 2s are given, so sometimes octave scale is also useful. We'll understand that is using the octave scale helpful or the decade scale. So here this 2 4. So basically they have also given the conversion, so they have given you everything basically. So let's start by understanding the slope differences. So these are the slope differences here. So let's understand the corner frequencies. So here I have one corner frequency. How much slope is changing? 6 dB per octave or plus 20 dB per octave. So obviously I have a 0 at this frequency. So first let me write the standard time constant format. K I will have. Okay, here also I'm saying that it is starting from what? It is starting from a like minus 6 dB per octave, the slope. So minus 20 dB per octave, 20 dB per decade. That means I have a single pole at the origin. So I have single pole at the origin. I have single pole. Okay. I have single pole at the origin. Then obviously I have a 0 at omega equals to 2. So 0. Then what else I have? Then slope increases again. So I have another 0 at omega equals to 4. So I have another 0 at omega. So here also you can understand that they have given you a few things. So you have 2 zeros and 3 poles from 4 poles. You can understand from here itself. But still, let's not use that. Let's use our basic things. So I have another 0 at omega equals to 4. Then after this, at omega equals to 8, I have a pole because the slope is reducing from plus 20 dB per decade to 0 dB per decade, or plus 6 dB per octave to 0 dB per octave. So I have a pole at omega equals to 8. After that, what is happening? After that, this is again further reducing. So at omega equals to 24, what is happening? My slope is becoming minus 6 dB per decade. So again I have pole at omega equals to 24. Next, again I have another pole at omega equals to minus 12. Another pole at omega equals to minus 12. Sorry, minus 36. Because here the slope is further reducing to minus 12 dB per octave. Okay, so it is ending at minus 12 dB per octave. That means the number of poles will be how much? Number of zeros minus number of poles should be equals to 2. Here number of zeros is 2, number of poles is 4, so total 2. Yeah, that is fine. This is correct. Now let's see this. So they have given you this location. This is what? S by 2. So omega equals to 2 is given. This is given, but this is not given. S by 4 is not given. Here this is A times S. So A equals to 1 by 4. Just remember that A is equals to 1 by 4, not 4. A is not 4. If this was given as S by A, then you could have written A equals to 4. So don't get confused by this. So A will be equals to 1 by 4. A will be equals to 1 by 4. Next, this 1 by 8 is given, fine. This 0 pole is also given. This B is not given. 36 is given here, but this 24 isn't given. So my B is equals to 1 by 24, not 24. So B is equals to 1 by 24. That is fine. Okay, all these things are fine. Okay. So yeah, this is fine. Now you have to find A by B into K. Now K we don't know. K we don't know. Obviously we can't put S equals to 0. That is difficult. But what we can do is, like this thing is that if we put the intersection of this line is 8 over here. The intersection of this line is 8 over here. So this is what we need to find. So how to find this one? So if you remember the formula, what was my formula? Like for K, formula for K was omega, formula for omega GC. Omega GC was K raised to power 1 by N, where N was the number of poles at the origin. Okay, if you remember, like when I had poles at the origin or something. So it, like, because all these things will be ignored, I'm talking about only this part. Okay, if let's say if the Bode plot for only this one is given, Bode plot for only this one is given. Omega. This was my omega GC, and this is my what? K by S. Here my slope is minus 20 dB per decade. Okay, if you remember the formula, okay, well and good. If you don't remember the formula, we can solve this simply. So this is my omega GC here. So like what we are doing is we're assuming, like that's why they have given this to find the value of K. So this and these are same. Okay, K value will start from here itself, right? K won't change for this line and this line. Like for this line and this line, the value of K won't change. So I will approximate my K from here instead of this, because finding K from here is difficult for me. So obviously I will approximate my K from here. So that's why I use this formula. Okay, if you don't want to use this formula, what you can do? You can simply use this thing, that like this is the formula. If you don't remember this formula, then simply use this. That what is the magnitude expression of this one? What is the magnitude expression of this one? So let me name this as G dash of S. So G H dash of J omega equals to K of omega. Now let me convert this into log format, or what you can do is, what is a unity gain frequency? It is basically where the gain is 1 equals to 1, where this equals to 1, so K will be equals to omega itself. If this was, let's say, square, so this will be omega square. So whatever you choose, so K is omega, and omega is given, omega GC is given, it is 8 radian per second. So our value of K will be 8. Okay, from here if you want to understand, from here if you want to understand, whatever you try to understand, that is well. So I would always recommend like mugging up the formula. You can do it from the concept itself. Okay, or what you can do, what else can you do? In dB scale, we can convert this into dB scale also. Basically taking the same thing only, log base 10K minus log 20 log base 10K omega equals to 0, because log base 10 1 is 0 always. So unity gain frequency is log is 0. So my this obviously, like from here also you can understand that, yeah, this is K equals to omega itself. Okay, so K equals to omega itself. Like if you want to do it in log scale, if you want to do it in omega scale, whatever scale you want to do, you can do. So here K is 8. Okay, K is omega. So K value we found out is 8. K value we found out is 8. So I hope you understand the K value for this graph. What they have given, they also want you to use this information, because anything else isn't given. So only you can find the value of K from this information itself. So K value for this graph and for this graph are same, because they're starting from the same point and the slopes are same. That is why, that is the reason. Okay, so K for this graph and this graph is same. Okay, you don't have to worry, because you are basically approximating it. So now we have to find the value of A by B into K. So A is 1 by 4. So what is A by B into K? So A is 1 by 4, B is 1 by 24, and K is 8. K is 8. So this becomes 3 by 4. So this becomes 0.75. Okay, so yeah, this is the answer. Basically the answer is this one. So this is what I meant by finding the value of K from the intersection of omega axis. This is what I meant here. Put the value of omega in the approximate transformation and equate it with 1. You can do unity value of frequency, you can do. Okay, put the value of omega, that also I meant. Okay, so simply that is what we did. Put the value of omega, we simply put the value of omega here, right? Put the value of omega and we found out value of K. Okay, that is what I meant. So let's do another question. So this is again another gate question. I am forgetting to write the years. Okay, this is another gate question, but this is I think 2016 IC Bangalore. Okay, so again, right, they have given you the Bode plot and you have to which one is the best approximated transformation basically for this given Bode plot. Now can we eliminate anything from the options? Again, this time the dB scale or decade scale is given. Okay, so here what we observe is like we have the slope changes here, so they haven't given information about the corner frequency. Here also they haven't given information of the corner frequency. So don't get confused by this. These are not my corner frequencies. These are not my corner frequencies. Okay, this is just they have given some information that at this point my magnitude is 0 dBs or my magnitude is 1 in absolute scale or decimal scale. So these are the information. 8 and 0.5 are not my corner frequencies. Just be careful about that. But what other option can I get is that I have a 0 initially. At s equals 0. So yeah, all of these, all these three have s equals 0 at s equals 0, but this doesn't have. So this one gets eliminated. Okay, this one gets eliminated. Next, here I have minus 40 dB per decade. So I have two poles at some location, which I don't know right now. Okay, so this also gets eliminated because here at some corner frequency I have two poles, this for sure, because this is 0 dB per decade, because here there is no slope change, but suddenly it becomes minus 5 dB per decade. So that means I have two poles at that location. So I have two poles at this location, but this is telling me that I have one pole at one of the corner frequencies. Like all of the corner frequencies, I have only one pole. That is not possible. Here I am seeing the slope changes 0 dB, like from plus 20 to 0 dB. That means I have one pole here and I have two poles here. That means this is wrong. This is wrong, because it is telling I will have always one pole at each corner frequency. No, here I have two poles at a corner frequency. So this is wrong. Only these two are correct. Like, I mean, these two can be my possible answers. Now, is this the answer? Let's check for the answer. Okay, so like this one also can't be the answer. Why this one can't be the answer? Because what this is telling me is that I have a corner frequency at omega equals to 0.25. Like this is the tau. 4 is the time constant. So 1 by tau is 0.25. This is telling me that I have a corner frequency at 0.25. Can I have a corner frequency at 0.25? This is always constant. Like slope is constant. Okay, slope is constant here. Slope isn't changing. So obviously this one is eliminated. Only option A is correct. Okay, so the option itself you can directly eliminate. Obviously now we'll solve this using the fair method. Okay, so how to solve this using the fair method? So let me first draw the this plot basically. So exam hall you can use that trick, but if you want to solve this fairly in your home, obviously you will use this one. Magnitude G of J omega n dBs. So plot we have been given something like this. And here we have 0.5 and here we have 8. Okay, and this is 0 dB. This is 0 dBs. One more information is given: the magnitude at this point, the magnitude at the corner frequency is given. The slope at the corner frequency, the corner frequency isn't given, but the magnitude at the corner frequency we know. So magnitude at the corner frequency is 12 dBs. Now, as one thing I'm observing, this is in multiples of 6. So whenever the magnitude is in multiple of 6, what I can do is I can convert this into octave scale. This is not mandatory, you don't need to do this, but as my magnitude is in the multiple of 6, I will do this. In simple decade scale also you will do this. Okay, we'll solve using both scales, but first I will solve it using the octave scale. So here I will convert this 20 dB per decade to octave scale, as I am observing that my magnitude is multiple of 6. So this becomes 6 dB per octave, and this becomes minus 12 dB per octave. Okay, so what can I say is that one thing very interesting fact, as I told you, right, multiple of 6. So what is the interesting fact here? As I move one octave, this will move up by 6 dBs. As I move another octave, this will move another by 6 dBs. So I'm observing, like here this is 12. Okay, that means I move total by from 0 to 12. 12 dBs I move. So if I move 12 dBs, how many octaves did I move? I move 2, because the slope is constant here. Slope is constant until here. So I move 2 octaves. So that is why I was converting it into octave scale. So this is let's say this is 1. So obviously octave means 2 times the previous frequency. So this will move here, the magnitude will become 6, another octave I've moved, the magnitude will become 12. Very simple. Now here what is happening? I am moving, like the slope is here minus 12 dB per octave, and from 12 dBs, like the magnitude still here is constant, from 12 dBs I'm going to 0. So total I am moving 12 dBs, and the slope is minus 12 dB per octave. So if I move by 12 dBs, that means it is moving to 0 dBs. Like in one octave I'm moving 12 dBs down. So in one octave I'm moving 12 dBs down. From 12 dB I'm going to 0. Yes, and this is also telling me that my slope is minus 12 dB per decade. So what is this distance? This distance is 1 octave. This distance is 1 octave. So if this distance is 1 octave, obviously here whatever the value will be there, this will be multiplied by 2. So this is 8, so this will be 4. So 4 times 2 is 8. So the slope here is minus 12 dB per decade octave. So if I move 1 octave, I should move down by 12 dBs. Is it happening? Yes. My magnitude is 12 here, and moving down by 12 dBs, magnitude becomes 0 at the 8 frequency as I move 1 octave. So obviously this is 12 dBs. So yeah, this is minus 12 dB per octave. Yeah, that is fine. So I got my corner frequencies from here. 2 and 4 are my corner frequencies. And value of k. What about the value of k? So for value of k, what you can do is, again you can use this. Again you can use this simply. Like I'm doing the shortcut here. Okay, k by omega. Like as I have a 1 0. So this time this is not by omega. This is k times omega, should be omega gc should be equals to 1, because at this frequency my magnitude is 0 dBs, or in a decimal scale 1. So what is omega gc is 0.5. Omega gc is 0.5. Okay, so k will be equals to 2. So don't get confused, like you equate this with this here. No, this is some other like value. This is going to, again magnitude is going again to 1, but this is a starting magnitude, right? That's why we equate with this one. Don't equate with 8. Don't equate with 8. Just be careful about that. The initial slope. The initial slope always gives me information about the k. Just remember, initial values, right? This doesn't give me information about the k. So k I got the corner frequency. Let's just write it in the standard time constant format. So g of h of s equals to 2 times, I have a 0, and after this I have only poles. I have. So one pole I have at s equals to 2. So s by 2 plus 1, and another pole I have at s equals to 4. It's equals to 4. I have another. Okay. So yeah, this is basically my transfer function. So you can equate it here. Okay, sorry, I have 2 poles here. Sorry, I have 2 poles because the slope is minus 40 dB per decade. So yeah, this is, you can equate this one. You are getting the correct answer. Now, should you do this in decade scale? Yes, you can. Obviously, you can do this in decade scale also. So like this was in octave scale. In decade scale, what do you do? Simply you do one thing, that you know the slope here, so you mark these points as A and B. Okay, you mark this point as AB. Now again use the simple slope formula. Like that is what I did here. You use the slope formula without writing it, because sometimes you don't need to write it. You can solve it just by seeing the graph. Okay, that is what I am trying to teach you. Just by seeing the graph, how can you find the corner frequency, all those things. Don't have to write anything, so that it saves time in other difficult questions. That is more important. Bode plot is very simple topic, so you have to save time here. Okay, so here this becomes slope AB equals to this YB. What is YB? YB is 12 dBs. So 12 minus 0 by log base 10 of omega B. I don't know the first corner frequency, this is, and omega this is 0.5, and this is what? This is 12. Sorry, this is 20. So 20 by 2, this is wait a second, omega p1 by 0.5 into log base 10 equals to 12 by 20. So this is 0.6. So omega p1 by 0.5 equals to 10 raised to power 0.6. Simple, I'm converting into log format. So this is 10 raised to power 0.6. What is 10 raised to power 0.6? If you remember correctly, it is simply 4, because just remember one thing, that 10 raised to power 0.3 is almost equal to this. You have to remember. Okay, anyhow you have to remember this, please. Okay, I'm begging you guys that you have to remember this. 10 raised to power 0.3 is 2. Now if you simply square this one, you will get 4. Square this one and this will become what, multiplied by 2, this is 2 square, so this will become 4. So omega p1 will be equals to 0.5 into 4, which is equals to 2 itself. Okay, 2 radian per second. And the same thing you do, same thing you apply here. So let me name this, like this is the slower process that I'm talking about. So C and D. Okay, C and D. We solved this using 3 methods. Basically, first the optional elimination, second is the octave scale, and third is the decade scale. So now again you write the slope basically. So now the slope is minus 40 dB per decade. So it is starting from like ending to 0 dBs and starting from 12. So 0 minus 12 divided by log of 10. Starting from that, so omega p2 will be here and ending to 8. Okay, and the slope here is minus 40. So yeah, slope here is minus 40. So this is minus 12 by omega p2. So here it becomes log of 10 8 by omega p2. Am I doing something wrong? Plus 20 is going to 0. Yeah, 8 minus correct minus 40 is correct. So this becomes 2 by 5 itself, isn't it? No, this becomes 3 by 5. 4, no 4, sorry, this becomes 3 by 10. Yeah, 3 by 10. This becomes 3 by 10 basically. 4 times 3 into 4 times 10. 3 by 10. Now this is omega p2 is equals to simply 8 by omega p2 is 10 raised to power 0.3. Again, I told you to remember 10 raised to power 0.3 is 2 itself. So omega p2 will be 8 by 2. Okay, now this is how you can identify the corner frequencies. Whatever like method you find suitable, use that method. Okay, so yeah, this was basically it for this question. So this is the most important lecture. Do try to repeat the lecture if you couldn't understand anything, because from here the main questions will come and you can do the questions in seconds. As I told you, right, you can just eliminate the options, or you can just use few formulas. If you don't want to use the formulas, don't need to use the formulas. You can directly equate this one. Don't need to use formulas. You can directly equate in the with the magnitude function itself, and the corner frequency you can easily identify, right? So all these things, have you got the idea how to convert into octave scale, how to convert into decade scale, all those things. So the most important lecture. And obviously remember few things, right? 10 raised to power 0.3 is 2, 10 raised to power 0.6 will be 4, because it is simply the square of that one. So yeah, this is it for this lecture, and I will see you in the next lecture with error in Bode plots and Bode plots for second order systems. So yeah, thank you for watching.